All right, so this video is going to be about oxidation processes. So first we'll introduce oxidizing agents, and then we'll go over some specific reactions. It's pretty much just epoxidation, though. So obviously we know a few oxidizing agents would be like oxygen or ozone, O3, and then maybe we know about hydrogen peroxide, H2O2. And these are some, I mean, they do work in organic chemistry, of course, but a few other ones are going to be very specific to organic chemistry reactions. So like epoxidation, for example. So this one right here is tert-butyl hydroperoxide. And so we still got that peroxide. And so it's going to be like a, let me draw you the structure real quick. So we've got the chicken foot, right? The tert-butyl. And then we've got a oxygen-oxygen single bond, and then that terminal oxygen is bound to a hydrogen. So it's very similar to hydrogen peroxide. Let me change that bond angle, sorry, just to make sure we're good on like the tetrahedral arrangement. Okay, and in addition to those oxidizing agents, we also have peroxy acids. It's just a class of compounds that have the general formula R with the almost like a carboxylic acid, but they got an extra oxygen in between. Okay, and so this one right here is peroxyacetic acid, and this one right here is super common. You should definitely familiarize yourself with this. This one is meta-chloro peroxybenzoic acid, okay? And this is usually abbreviated MCPBA, okay? So little m and then big CPBA, okay? Meta-chloroperoxybenzoic acid. And the meta, I mentioned it before, is because the substituents are basically out at a 1-3 position. So the 1-2 position, that the 2 position would be ortho, 3 would be meta, and then 4 would be para. And that's pretty much how we classify substituents on a benzene ring. So this chloro is in the 3 position, aka meta. All right, so there are a class of oxidizing metal compounds as well, and these, in my opinion, are very obvious that they do the job of oxidizing things. And so we have Na2Cr2O7 as well as the equivalent of potassium salt. Okay, and this is sodium or, sorry, I'm going to write it in blue just to kind of give it that pop. So sodium or potassium dichromate. So you got 2 chromiums in there, so that's kind of how I think of it. Dichromate. Okay. The next one, you might see a chromium like with 3 oxygen. All right, and last but not least, silver oxide. So Ag2O, it's kind of got the structure similar to water, but the hydrogens are replaced with the silver. So silver oxide. Now, that's all the ones that I want to introduce to you in terms of oxidizing agents, but take a look at all of them. Like, what do they all have in common? They got tons of oxygens, right? Just loads of them, buttloads of them. And so it's very obvious that they're probably going to oxidize something, okay? So what do they actually do? So whenever I think of that, I always think of Kindergarten Cop. Who is your daddy and what does he do? Everybody get down. We about to oxidize something. Get to the chopper. And we're going to oxidize. Remember the... I'm sorry, I went way too long with that. I'm sorry. Kindergarten Cop. If you haven't seen it, it's fantastic. Oxidation is the increase in CZ bonds and decrease in CH bonds. We already knew that, right? So let's oxidize in alkene. See what we can get here. So a variety of compounds, just to sum it up. But an epoxide, of course, is definitely increasing the number of CO bonds. We can also throw some alcohols on there, right? And we can do it in a couple different ways as well. So we're not just throwing alcohols on there willy-nilly. We can be very selective with that one. And then we can also split that carbon-carbon double bond to replace with oxygen bonds. And then, of course, our alkynes can just be done similarly to give us carboxylic acids. And then we can also oxidize alcohols. And that's going to basically increase the number of carbon-oxygen bonds. And that gives us ketones and carboxylic acids. So this is more or less what we're looking at for the entire chapter. Let's focus on that those epoxides first. Okay, so epoxidation, and you're stoked because epoxidation is a reaction that we're already familiar with, but this is done in a very different way. So you'll add more tools to your synthetic toolbox for sure. So here we go. We've got these peroxy acids, right? MCPPA, and then the acetic acid one. And when those are combined with an alkene, we get an epoxide. Long story short, right? So remember, epoxides and stereochemistry do matter. Let's say we labeled them with R primed, etc. Then this would be our final product. However, we could get the other isomer and have the epoxide pretty much at the bottom with the R groups projected in the general same direction. So the wedge is the same R group, and then the dash is the same R groups as well. So, but it's just pointed in an upward direction. So if you rotate that molecule, what you end up getting is, let's write all our R groups. And when I say rotate that molecule, I mean basically take that lower oxygen and then almost like pull it out of the page and then place it back on the page, but on the top. Okay. So what that's going to do is that places the R prime and R double prime in the front now. Those are not the same as on the left, right? And so basically the configuration of these two carbons, which are, if R and R prime, etc., are different, then they are enantiomers, okay? Because we switch the configuration, and by definition, that's what our enantiomers are going to be. They're non-superimposable mirror images of one another. And you can definitely check that. Draw your mirrors, draw your compounds, and double check for yourself. But they're enantiomers, okay? Now, what's the mechanism of this bad boy? Now, this one's fun, all right? So I'm just going to put that R group in there. It's going to represent this benzene ring as well as that methyl group, okay? All right, let's try and color code this so we can kind of follow the flow of electrons. So those blue, it's kind of like the bromination. So the oxygen attacks the alkene carbon, but also gets attacked by the pi bond. And then when we do that, we're breaking a bond to create another carbon-oxygen double bond, which breaks the carbon-oxygen double bond to swoop on that proton. Okay, so it's like a little... I don't know. It's like a little do-si-do. We're hanging out, we're dancing, we're sharing partners, and we're making fancy things, right? We're making epoxides here, and so you're gonna have to follow the flow of electrons. It's really hard for me to kind of not be able to point directly, but I'm trying to label these electrons and those bonds with red. I got the black lone pair, so you know where that the red and black arrows represent those where those electrons went to create those bonds. And then we also have the pink ones representing those arrows that kind of created the oxygen and hydrogen bond, and then the carbon oxygen double bond. Okay, so just follow the flow of electrons, and I think you'll be all right. We're pros at this stuff now. So uh, that's the mechanism. It's all occurring all at the same time, also known as a concerted mechanism, right? And here's the thing. So I drew it all color coded, but really what the bottom right is to represent just that's the product drawn normally. Okay, so you end up with the carboxylic acid and as well. So if we add wedges and dashes to the alkene, what I'm trying to show you is that it's flat. Okay, and that peroxy acid is approaching from the top, but we can also draw a molecule approaching from the bottom. And what that does is it results in our two enantiomer products. Okay, and that's how you get the two products. Okay, so anytime you see MCPBA or the peroxyacetic acid, then you're thinking, if I got an alkene, I'm about to make an epoxide, and I get two different isomers. Okay, and that's the idea of stereospecificity. We for like cis and trans alkenes, we yield different stereoisomers, and so this is a concept that we've already learned, right? We saw this when we did the bromination of cis and trans alkenes. Okay, so remember that time when we did that thing. So here you go. I'm about to do it again for you. So cis alkene, you remember it's anti-addition because we got that bromonium ion intermediate, and that means we're essentially adding wedge and dash bromines to that alkene. And what we get here is enantiomers. Fancy, right? Actually, that's not fancy. That's totally expected, I think. But when you throw in the trans alkene, you get the fancy answer because you end up getting, you got your wedge and your dashes and you swap them for the addition of those bromines. But remember, these guys are identical compounds because they are a meso. And that's fancy, my friends. I'm sorry. But same thing applies when we're doing epoxidation, right? So here's my attempt at drawing a flat alkene. I think that's terrible. I'm sorry. It almost looks like the Under Armour symbol, but that's cool. Whatever. There's a cis alkene right here, and then we got the trans alkene. Oh my gosh, that looks so bad. I'm just gonna let it be. Let it be, let it be. All right, cool. That's a trans alkene. And I'm sorry. I'm actually pretty good at drawing, but apparently not always. So I like to use when I give my examples, I'm pretty much just going to use MCPBA because I can just draw that rather than drawing out that BS peroxyacetic acid formula. So sorry. Remember, they're one and the same in terms of the reactivity and making epoxides. And so we got that cis alkene that gives you these two isomers. Let's check out the relationship though, right? So if we throw MCPBA at this cis alkene, what are the two epoxides? What's the relationship between them? We can kind of flip them over. We can also I'm drawing it two different ways just to kind of show you that I didn't really I don't know, I jumped straight to the after the rotation, but if you approach from the bottom or the top, you get these two compounds, at least the way they're drawn, and then if you rotate on that vertical axis, the way it's drawn, you get the same exact compound, okay? So those are identical compounds. All right, so what do we get when we have transalkene and we throw MCPBA at it? So again, we approach from the top and we get the oxygen on the top, and then if we throw it on the bottom, we'll still get the methyls as a wedge and a dash. Sorry if that wasn't clear the way I did it initially. And then if you rotate, you end up with the wedge on the right and the dash on the left. And then if you were to rotate on that vertical axis, let's see, is that clear how we're doing that? We're rotating on that vertical axis. If we did that, we would end up with a different compound, right? So the rotation doesn't yield the other product. So what is the relationship between the two? Well, they're enantiomers, okay? And so that's, again, very much related to the bromination of cis and transalkenes. So one of them yielded enantiomers, and the other yielded identical meso compounds, okay? So here's the thing, though. Notice that the trans led to enantiomers in the epoxidation, but not in the bromination. So it's not all about memorization. Just know the mechanism, and then you can get to the product, and you're good to go. Okay? So to fill in that horrible looking chart, MCPBA gets you an epoxide. Okay? And the key thing we really want to remember is that it's all about syn addition. So that's kind of silly to mention in my opinion, because we can't have an oxygen bonded to both of those carbons, but also like kind of almost being bound across. Like you can't have it on the top and the bottom. That's silly talk, okay? But syn addition in terms of vocabulary, if you want to discuss it, okay? Now, the next thing to talk about is actually really cool. I love enantioselective reactions. As you can imagine, I always talk about how like stereochemistry is really important and how our bodies are like lock and key. So if you're making pharmaceutical drugs, then you really want to make sure that you can be you can isolate a pure enantiomer. And so the best way to do that is to make, and especially the best way to do it and get your money's worth is to make a single enantiomer. And that's really what enantioselective reactions are all about. Okay. And so I just kind of redrew out this reaction. So we know that transalkenes kind of gives you these two enantiomers, right? And it's a 50-50 mixture. That's kind of the idea. That's, you can approach from the top or the bottom in equal, statistically equal. And so you're going to get a mixture of two different enantiomers, but that's not very economical. You're wasting money. You're throwing out half of your money, right? So because you're throwing out half of your product if you only want one enantiomer. So again, enantioselective reactions are all that's what the money is. If you can make super important things and be like 99% purity, you're golden. Okay, so enantioselective reactions afford predominantly one enantiomer or exclusively one enantiomer. All right, so actually let me like highlight this because this is a really important point. I mean, obviously it's the definition of enantioselective reactions, and again, it's related to like enantiomeric excess and things like that, which we have talked about before. And so obviously we're going to talk about an epoxidation reaction that's enantioselective, okay? And so it's not, I mean, enantioselectivity is really difficult to achieve. And so for Sharpless to actually achieve this with allylic alcohols, he kind of won the Nobel Prize doing it. And so that just tells you how important it is and also how difficult it is. And so using an allylic alcohol, we can get essentially, if we have Sharpless reagents, we can get 97.5% one enantiomer, just as an example on this particular reaction. Okay, and that means that we really only have 2.5% of the other enantiomer, not a 50-50 mixture. And that's crazy. That's awesome. That's great because again, when you're making pharmaceuticals, one enantiomer could be the active drug that can save lives, and the other enantiomer can be the exact opposite, which will straight up ruin your life. Okay. Um, Now I just want to remind you that basically this highlighted blue portion is the allylic alcohol portion. Okay. So it's if that OH was bound to the double bond directly to the carbon, that would be a vinylic alcohol. But since it's got the sp3 carbon spacer, that's allylic alcohol. Okay. And what are the Sharpless reagents? Well, you kind of have to know them. And so that's this tert-butyl hydroperoxide. Sorry. Um, and that can be abbreviated as CH3COOH. Okay. Then we have this titanium compound as well. So this titanium has this isopropoxide on it. It's got 4 of them, and it looks like this for the most part. So um, just it's kind of like isopropanol without the hydrogen, and then that alkoxide is attached to the titanium. Okay, let me move this down here real quick. Might as well move this titanium formula as well. So let's see. All right, sorry, just trying to get it organized, make it look better on the notes as well. All right, and so the other portion of these Sharpless reagents is this diethyl tartrate. Okay, and those OHs, you can see they are at chiral centers, and the 2 wedges gives you the RR conformation or configuration, and the plus sign, remember, means that it's dextrorotatory, so it rotates plane polarized right, plane polarized light to the right. Okay, and it can be abbreviated positive DET. Okay, and if we change those to wedges like this, then we get the negative SS diethyl tartrate and or negative DET. Okay, and that's really how you don't draw out or write out diethyl tartrate. You just put plus or minus DET on that reaction arrow with maybe the titanium and the tert-butyl hydroperoxide. Or I could just put like Sharpless reagents and DET, and then you specify which one. Okay. So let's say we had the Sharpless reagents with, do we want positive or negative DET? Well, let's do negative. Sorry, let me erase this real quick. Let's do negative, so that way we can kind of show you how we got to the 97.5% product on top. Copy and paste that real quick. Bada bing, bada boom. So here's the thing. That is very specific to the negative DET. So the fact that diethyl tartrate is chiral and it has all those oxygens, basically that affects how the allylic alcohol interacts with the metal center where as well as the tert-butyl hydroperoxide. So the tert-butyl hydroperoxide essentially can only approach it from one side because of the way it's interacting with the DET. Okay, and so that's really all it is about. That's the idea in general about enantioselective reactions, is that you have a chiral catalyst like the titanium and the DET all combined together with the tert-butyl hydroperoxide, and they interact with one another in a manner that only allows the tert-butyl hydroperoxide to approach from one side or the other. And that really comes down to the fact that the DET is chiral, and we have the 2 different enantiomers to allow us to kind of approach from the top or the bottom. Okay, and so I like to think, the way I think of it, if you had a question, is DET, negative DET means like you're going down. If you're a downer if you're negative, right? And so if the arrow means that this oxygen is coming down on this alkene, and that's why we get the oxygen epoxide the epoxide with the oxygen on top. But the positive one, it's like you're moving up, you're coming up on the world. and that's why the oxygen is kind of on the bottom. It's approaching, it's moving up. Okay, I'm not sure if that's gonna help you, but hopefully you get what I'm saying. Um, and yeah, that's pretty much it. Let's do an example, and it's pretty straightforward, I think. So that will be it. Um, mind my don't mind my drawing. My drawings are terrible right now. I don't know what's going on. So we have this allylic alcohol, right? And so we really want to just try and figure out what the product is, or we can figure out what we started with to get the product, right? And so in this case, I'm going to draw this product for you, and I want you to tell me which Sharpless reagents I used. So obviously the terbutyl hydroperoxide at the titanium, tetra isopropoxide is always going to be the one used, but are we using positive or negative DET? Now remember, negative means we're coming down, right? So we're coming down, and that oxygen sits right on top of that alkene to give that stereochemistry right there. And so we use negative diethyl tartrate, okay? As well as our terbutyl hydroperoxide and our titanium compound. So there you have it. I mean, we could also predict what the products would be with the given alkene and the Sharpless reagents, right? So, for example, let's just draw this alkene right here. We got some Sharpless reagents and positive. Nope. Yeah, let's go with positive DET. Okay. What's the product? Here's the thing. You have to orient the allylic alcohol always, so it looks like this. So you have your alkene, and then your allylic alcohol is projected like to the back, right? Or upper right when we're looking at it in terms of an alkene, okay? And this is all, again, I can't stress enough. Always has to be oriented to the upper right in order for this positive DET and negative DET kind of approach. So like I say, negative DET comes from the top and goes down, and positive DET goes up. That stereochemistry is dictated by the presence of the oxygen being on the upper right. Okay, and so that positive DET, that's why we had to rotate the whole molecule to just show that it's in the upper right. And then now we can say, okay, since it's positive DET, we can put the oxygen on the bottom. And that's what I have it as a wedge, as a dash, sorry. All right, so I know you're going to have some questions, so just bring them. Shoot me an email, come to office hours, shoot me a text. Just kidding, none of you have my phone number. Don't text me. But yeah, have fun with it. I think in general, it's pretty chill, except for maybe the idea of enantioselective reactions, but it's an extremely small portion of this book, okay? Have fun.